section. So we have Nick on stage with an introduction to Cython and how to speed up your Python code. Please welcome Nick.
Thank you. So, yes, a Cython walkthrough. I'm Nick Murdoch. I won't say too much about myself. I've been doing Python since it was version 2.4 or something like that. Of that, I've done about 9 years of C, and I've also used Cython and its predecessor Pyrex for those 9 years as well. One thing I just want to clarify is that I'm not a contributor to Cython. I just use it, so apologies to the Cython team if I've made any major mistakes. So, what is Cython? At the most basic level, it's a programming language, just like Python is. In fact, it looks a lot like Python, smells a lot like Python, and so on. But it has a few extra features that we will have a look at. So, Cython takes a Python source code file or a Cython source code file and converts it into a C source code file, which can be compiled into a compiled module that Python can then import using exactly the mechanisms you'd expect, the import statement and so on. There's 3 use cases for Cython that we're going to have a look at in this talk. The first one is to speed up existing Python code. The second one is to call Python from a C program. And the third is to do the opposite, call C from a Python program. So let's have a look at the first one. We're going to have an example problem for this section. And it's going to be writing a function that finds the maximum product of n consecutive digits in a list. So for example, if n is 3 and your list is 623654, you can see that the 3 consecutive digits are the final one. The final 3, 6, 5 and 4 have the highest product, so we return 120 as a result. Let's have a quick look at how this has been implemented in Python. So we've got a function definition, big product, takes digits as a list of integers, and n as another integer. It keeps a track of what the best product we've seen so far is, and then it loops over the digits in order and takes a block of digits of n size, multiplies those up, and if that product is better than the best one we've seen so far, we assign that to the best variable, which we return at the end. Now this is a fairly naive implementation. There's obviously some improvements that we've made to that, but the important thing here is that we've got 2 for loops and a bit of maths in there. So let's put down a baseline run, stick it an array, run it 1,000 times, and it gives us 0.9 seconds. So that's our baseline, and we'll see how much we can beat that with Cython. So again, the idea of Cython is to compile a Py file into C, and then that C file gets compiled down into a compiled source code. There's several ways you can do that with Cython. You can either try and compile it by hand if you really want to. There are plugins for Jupyter Notebook and that sort of thing, or even just the interactive interpreter. But the way I'm going to show you is using setup.py, which you've probably used in your own projects. The setup.py will look exactly the same as a normal setup.py will look, except you have one extra line from Cython.build import Cythonize. And at the end of the setup call, you add ext modules equals Cythonize, and then the name of the Python file that you want to compile. And then you can install that module using pip install or setup.py install, or however you prefer to do it. And it will make sure that not only is it compiled to C, it's also compiled to that final compiled module that you can import. So with no changes to the code at all, except for those 2 lines in setup.py, we're down to 0.6 seconds for the same inputs. And I think that's not bad for 2 extra lines in your setup.py. But we can do better. We need to look at what's taken the most time in that Python file. Well, it's Python, unfortunately. Python's a very powerful language and lovely to work with, but the cost of that is slightly slower runtime than a compiled language would be. So we need to find where the most calls into Cython are. And Cython provides us a handy utility to do this. There's a Cython command line program, and if you hand it the -a switch along with your Python file, it creates an HTML file which can then be inspected, which we'll do now. So as it says, yellow lines hint at Python interaction. Click on a line that starts with a plus to see the C code that Cython has generated for it. So yes, as it says, we've got various different shades of yellow there. The lighter yellows are less interaction with Python, and the deeper shades of yellow indicate that much more work is being done in the Python layer. And you can click on each of these lines. So if we take one of the lighter yellow lines as an example, and click on product equals 1, it expands out into what the equivalent C is. And this is C that would literally be in that compiled Cythonized file. So it's taken the object in Python that represents the integer number 1, because everything in Python is an object. It's incrementing the reference count for it, because Python uses reference counting for the most part for deletions and so on. And then it assigns it to the object that we have called product. So that's what a simple line does. We'll have a look at one of the deeper yellow ones now for j in range n. Now, if you're writing C straight up, you might expect to write something like for j equals 0, j is less than n, j++, and leave it at that. But if we click on this, we can see what Cython generates for it, and it's quite a lot. So don't worry, I'm not going to make you read all of that. But briefly, what it's doing is that it's calling into Python, and it's passing the built-in range function, which, don't forget, in Python we can override if we really want to, and the object that we call n. We're getting the result of that back. We then have to call getIter on that resulting object to get an iterator object. Then we have an unbounded for loop. The first line of that, more or less, is getIterNext on that iterator to actually get the Python object j. We then have to check with Python, because in C we don't have exceptions, so we have to ask Python every Python call whether there was an exception. If there was an error and it was a stop iteration, then we have to break. Otherwise, we actually finally get on with the rest of the block. That's obviously a lot more work than a standard C for loop. There's also a lot of optimizations in that big block of code I showed you that deal with lists and tuples, as Python has some faster APIs to get into those. So the next thing we have to do, or the next thing we were going to show you, is converting bigproduct.py into bigproduct.pyx, which is the file extension for a Cython file. And we're going to convert as many of the Python objects into C objects, into C types as possible. So the first line we're going to have a look at is the function header, bigproduct. We're going to turn the n into an unsigned int type by introducing this extra syntax that Cython supports, literally just adding unsigned int in front of the variable name. And now, whenever we call into this object from Python, Cython will automatically convert the Python object that you've passed it into an unsigned int if it can, and raise a type error if it can't. Secondly, we'll convert the INJ loop parameters into the C size T type, and for that we introduce the cdef syntax, which declares the types at the start of the function, just as you would expect to do in C. We'll convert digit, which is our multiplier variable, into an unsigned int, and we'll convert product and the best product, which we'll be returning, to an unsigned long. Again, when we return that unsigned long, Cython converts that back into a Python object for us. So Python will get a regular, probably an integer. The only variable we haven't converted is the digits list. I mean, we are interacting with Python at some level, so we do have to actually keep some Python in there. But that's not bad. We've converted pretty much everything that we can there. And indeed, if we look at the Cython-A output, it's become a lot less yellow. If we were to have a look at the j in range n line, then we'd see that was actually a normal C loop now that does the int j equals 0, j less than 0, j++, j less than n, j++. So let's have a look and see how that has affected the speed. So pure Python gave us 0.9 seconds. Cython with no changes gave us 0.6. And Cython, if we've fully converted everything that we can, we get 0.06. So it's pretty good. It's not too much work and more than a tenth better. So let's move on to the second use case, calling into Python from an existing C application. There's several reasons you might want to do this. Perhaps you've got a C code base and you want to be able to write plugins for it or customizable tasks using Python because it's faster to develop that way. Or maybe you just want to prototype a feature in your C program and you want to write it in Python because that's going to be faster and you can convert it later into C if it works out. So in this example, we're going to create a command line program called Cython walkthrough, and we're going to use three files, two of which get compiled into that application, which are main.c containing C source code, and portal.pyx, which contains the Cython source code. Those two files will then together call out to our snake.py file, which can be a Python module, or if it's on sys.path, it will just get imported there. Anything that would import snake can be there, and we can change that after we've compiled the rest of the stuff together. I'm not going to show you the make files that are used for that. They're in the code repository if you want to have a look at them, but we're tight on time already this talk, so I'll leave that for you to do later. So yes, snake.py will be freely editable afterwards, even after we've compiled Cython walkthrough, and freely swappable out with anything that can be imported using import snake. So let's have a look and see what's in some of those files. In snake.py, I'm defining just a simple function called combine. It takes A and B as parameters. It prints out hello from Python, just as proof we're in Python. And as an example, it returns A to the power of B. Again, this could just be a placeholder, and you could implement all of your Python later if you wanted to. In portal.pyx, we're now introducing quite a lot more Cython-specific syntax. But the first thing we do is import snake, and as I said, it will pull in snake.py if that's on the path, or a module that's been installed called snake, whatever you like. The second line, we have to declare a function that's a C function rather than a Python function because we're going to be calling it from C. So rather than def, we start off with cdef. We also declare it as public because we're going to be referencing it from outside the portal.pyx file. Its return type is int. It's called entrance. It takes two parameters, int a and int b. And then finally, the except -1 at the end of that function header tells Cython that if anywhere in the body of the method a Python function is raised and not caught, it will immediately exit with the value of -1. So again, in C, no exceptions. You have to check the return value of everything as you go along. And that will be our error value, as it were. Print hello from Cython, just as proof, and then return snake.combine A and B. Again, Cython will convert those C integers A and B into Python objects for the snake.py combine, and it will also convert the output of snake.combine into that int return type for us automatically. So finally, let's have a look at main.c. And don't worry, this is the only C that's going to be in this presentation, and I'll go through it line by line. So first thing we do is include python.h, because we're using Python. Secondly, we'll include portal.h, which is generated by Cython from portal.pyx because we've declared a public method inside it. Int main is the entry point for command line programs into a C application. And then we also declare the result of the entrance/combine call as an integer. So print off hello from C, just to prove it, and then 3 extra lines here. I'm not going to go into what they do too much, but essentially they are initializing Python and doing all the necessary work for portal.pyx to work correctly. Those are pulled pretty much as is from the cython.org documentation. You don't really need to know what they do unless you're planning on doing particularly advanced things. Here we actually get to the result and the call into that function that we declared in portal.pyx, which calls out to snake.combine, which returns a value which gets converted to a C, and we assign that to the result object. And we're calling it with 1 and 2 just as dummy values in this talk. Then we'll print out what the result is. And finally, before exiting, we'll call pyfinalize, which does all the kind of memory management stuff that, that Python needs, and make sure that, that Python's all happy. So configure and make. Again, those are in the code repository if you want to have a look at them. They're not too tricky. Call Cython walkthrough, and we get the output hello from C. Then it goes up to Cython, hello from Cython. Then it goes up to Python, hello from Python, and then back down with the result and gets printed out. So use case number 3. That's the opposite. Call C from Python. So what C can you call from Python? In short, pretty much anything you've got that's been compiled or otherwise. You can include C in your Python project, and setup.py knows how to compile those into shared objects if you want to do that. You might want to use an external library, one that you've installed from someone else that provides header files. In fact, you can use anything that uses C or C++ header files. So that pretty much covers every compiled language I thought to look up. So Fortran allows you to provide C header files. I think Rust and Go also can. And I'm sure others can as well. So the example we're going to use for this slide, for this section, is we're going to draw a picture using the libgd library, which is a simple graphics drawing library. It's available from the URL up there. Once we've installed that, we're going to create a setup.py for our project. And the only change we have to really make to the setup.py that we saw earlier is that we just have to add that libraries equals GD line there. And now setup.py handles linking with libgd. And if you've ever written a makefile, then you'll know how much time that will potentially save you. Let's have a look at the implementation of gd.pyx, which is going to be our wrapper around libgd that we can call from Python. The first line is that we introduce this cdef extern from gd.h magic line. This is essentially the equivalent of your include gd.h in a C file, but Cython needs to be told what the C functions look like specifically, so that it can generate the correct C code. They should match reasonably well with the C headers. They don't have to match exactly, but they should mention the right types and that sort of thing. There are tools that will take C header files and generate these Cython definitions for you, but we'll go through them by hand just for this example. So there are two structures in libgd that we're going to be interested in for this quick wrapper. The first thing is GD image struct, which contains the actual image data and metadata. And the second is the GD point struct, which contains XY coordinates that will be used to refer to specific pixels in the image. As you can see, if we're not interested in the contents of those structures, we don't have to include them. And in fact, we only have to include the members that we actually intend to use. If GD point has extra members in it, we don't care. We're not going to be using them. Finally, we'll declare the functions that we're actually going to be using from libgd. So there's GD image create, which allocates the memory for a GD image pointer. GD image destroy, which does the opposite and frees up the memory. And GD image fill polygon, which takes the image and a list of vertices as GD point structures and draws a filled polygon object onto the image. Now you might notice that the GD image destroy and GD image fill polygon functions in particular take a GD image pointer as their first parameter. That's a fairly standard idiom for a lot of C libraries that interface with structure pointers. And I always think it looks a little bit like how we put self at the start of Python methods. So to that end, we're going to have an image class that wraps these functions. It's going to be a special class. It's going to be a cdef class. And this allows us to add a GD image pointer variable as class variable as part of that class that gets created for every instance of this class that we create. We then create a function called cinit, which is the equivalent in Cython to a regular init function. The main difference is that it's guaranteed to be called once and only once. In Python, there's various ways you can cheat and not have init be called, or be called several times if you really want to. In that, we can do memory management stuff because we know that we're going to get called exactly once. So we call gd_image_create with our size x and size y parameters, and we assign the result of that call into that C object member of the class. Now this is C, so again, there's no exceptions. We have to check the result of we have to check the result of that gd_image_create call to check that we didn't run out of memory, and if we did, we raise a Python memory error. The opposite of cinit is dealloc. So again, this is called when the instance is destroyed, and we simply just call gd_image_destroy, so we don't have a memory leak when we delete that Python object. Finally, we'll implement the fillPolygon method as a wrapper around gd_image fillPolygon. It's going to take a list of points as 2 tuples representing the vertices of the polygon, and we'll pass it a color as well because colors are pretty. Let's have a look at how that's implemented. So the first line is that we have to convert the Python points list into a C points array. We can do that using the standard C memory allocation utils, so calloc, malloc. You can even use Python's own memory allocation functions if you really want to. Pass it length of the points that we want to create and size of GD point, and then we get, we hopefully get some memory back. If we don't, then we raise the memory error again. Now, really importantly, we have to wrap the rest of the function in a try finally clause, because whatever happens, we need to make sure that we free that C points array, otherwise we've got a memory leak. Getting to the actual implementation, for I point and numeric points, we just copy the values from those Python points into the X and Y members of the structures that we've just created as C points. And then eventually we actually get around to calling gd_image_fillPolygon. Self.c object is the first parameter, C points is the second, and so on and so forth. So we'll compile that down with setup.py. We get a nice shared object that we can import into Python in the usual ways. And as an example, we're going to use plain Python to import that module and create an image. We get a regular Python object back, which we can call methods on, fillPolygon. And I've also taken the liberty of implementing an image.dump method, which writes it out to a file, because it's nice to be able to see what you've done. Just as proof that actually works, there's a resulting image. Relevant. Yes, hopefully in this talk we've seen how we can mix Python C in varying quantities to achieve what we want to. In terms of alternatives, I know there was a talk on PyPy earlier today. That's really good at making existing Python code fast. In terms of calling C from Python, you can have a look at the built-in C-types library and the CFFI library. But there's nothing I know of that can facilitate calling into Python from C short of writing a lot of C that interfaces with Python C API, which hopefully I've shown there is a good alternative to if you don't fancy wading through lots of C. So thank you for your time. Codes and slides are up on GitHub there. I don't think I'm going to have time for questions, but I'm around for the rest of the conference, so come and grab me. I'm on Slack as well, or Twitter. I'm happy to answer any questions. So, thank you very much.
Thanks, Nick. We do have time for a very quick question if you want.
Okay, yeah, I'll take one.
Anyone? Yeah.
You mentioned about the memory management between, you can use calloc or you could use Python's own memory management.
Yep.
What would you say would be the pros and cons, and what would determine which one you would use?
Mm-hmm. For the presentation, I used the standard ones because hopefully they'd be more recognizable, but it's recommended to actually use the Python ones where possible because Python's memory allocation means that Python can track what your how much memory is being used by Python, which is important in a bunch of situations. And it's also better at allocating small amounts of memory as well, I think. So it's better to use that one if you can, but you're welcome to use the C ones if your library prefers them or any other reason you choose.
Thank you very much again.
Great.